key property that is going to give you extra memory in your design. So what is the gating? Now, I'm going to explain the gating in details, but first, before we go ahead with gating, just let's consider one dummy example. So the dummy example here I have is, we want to get back to the story we had, Yulia winning something, right? And now I want to show you how you can think about the gating. Now, when we do basic RNN, you essentially start with your first word in the sentence, you compute the output, which is the next word, and you keep on going towards the end, right? And yeah, HT is the guy which is carrying the memory, right? So every time that you are going to talk about the next word, you are going to look at HT, right? So if I want to tell you what is the next word in the sentence, I'm going to look at HT. And hopefully HT is just gone long over the sequence, right? And then it has carried all the information, right? So that was the idea that we made the RNN, right? Now let's just think about our example we had. Yulia has been nominated to receive blah, blah. And then what we wanted to do, we wanted to just complete the sentence after 4, right? And we said if we want to talk about 4, what comes after 4, we want to put a pronoun, but we need to know who we are talking about, right? And if we know it's Yulia, then we're going to put it her, right? But if we have lost this point that Yulia was the one we are talking about, we're not able to find out what is the right pronoun here, right? You remember this example, right? Now, the thing that you would do, in this architecture, is that when you get here, you hope that this HT is containing some information about Yulia, right? So you're still remembering that Yulia is the one that you're talking about, right? But if you're training a basic RNN, and Yulia has happened far before, right? Now, at this point, when you start to update your weight, right, Yulia is not having any participation in the gradient, right? Meaning that when you keep on updating, never Yulia shows up in the learning process. And there is no reason for your neural network to pay attention on that particular time and Yulia, right? So that is the problem that could happen. If Yulia is still far away, even though theoretically your HT is containing some information about Yulia, but since you're doing backpropagation and it happened long before, it does not participate in the learning, that practically never happens. Now, obviously you cannot find out that this is Yulia if that is happening long before. And let's just now consider one other experiment. In this experiment, at every single time, I'm going to define one new variable. I call it UT, okay? And this UT is either 1 or 0. It could be any number between 0 and 1, but let's say it's either 0 and 1, okay? Now, I am going over my sequence, and I get to the time where Yulia is happening, right? Now, when I see the word Yulia, I put, that is time t0, and I put this u value at t0 to be 1, okay? So u, this extra auxiliary variable I defined, is being 1 now, okay? Now, how do I update my memory then? I'm going to update my memory in this form. Let me first do it for the memory. I'm going to update it this way. I'm going to compute whatever I had as before, right? So the previous memory multiplied with its own weight. Look at line 2, item 2 here. Previous memory times its own weight, input times its own weight, activated, right? But I do not directly pass this guy to the output. So I'm going to call it h tilde, and looking at h tilde, I compute h as in line 3. How do I do that? I'm going to compute ht as h tilde times this auxiliary variable u that I had plus 1 minus u ht minus 1, right? Everybody's cool? So it's a kind of moving average. You see that? Yeah? Now, let's do one example here. If u is 1, what's going to happen? What would be ht? It's going to be exactly h tilde, right? H tilde going to pass times 1. 1 minus 1 is 0, so HT is not going to pass, right? But what if UT is 0? What's going to happen? What's going to be HT? HT minus 1. So it means that I ignore whatever I have computed at this time, right? And I copy whatever I had at a memory in the previous time to this time. Make sense? You see that? Okay, now the trick that I'm doing, I'm going to set U at the time Julia happens, I'm going to put it 1, right? And for any time after Julia, I put it to be 0. Okay? Everybody's cool? Now let's see what's going to happen. If I am going over my sequence and then I get to the point where Julia is happening, right? So I'm going to say that I'm going to compute my memory in this form, right? So this memory is having some, of course, memory from before, and it's going to have xt0. And xt0 is the token which contains Julia, right? So xt0 is fresh information about Julia, right? I compute h tilde at that time, right? That h tilde is computed out of this input, Julia, so it's going to contain fresh memory of Julia. Everybody agrees? Yes? So h tilde has fresh memory about Julia, then I have set u to be 1 at this time, right? This means that my memory is going to get updated exactly the fresh information about Julia, right? So that is going to be my memory. So my memory at time t0 is directly computed from the word Julia, right? Everybody's cool? Yes?
Why doesn't it happen with our WM? Why doesn't WM learn, okay, now this is the important word, so I should give it more weightage and kind of discard everything?
Yeah, but if you do that, I mean, we're going to get more detail into gating, but if you just work with WM directly, then you're going to get again into the issue of vanishing gradient, right? So this guy is just, you're going to see that it's somehow skipping time. Everybody's cool? You see what happened? Yes?
How does the network know that when the x is Julia, then it sets u to be 1?
We do it later. So we need to learn it as well. We're going to find it. Yeah. But right now I assume that it's a geniated information. Like I do know that I have it 1. Okay? Everybody's cool? Now, what's going to happen in the next time? Well, if I go in the next time, the next word is happening. So my h tilde is going to be computed in terms of that new word, right? And it's going to have the impact of Julia less stressed, right? Because Julia now is in its memory term, right? But if I have my u to be 0 in the next time, then the memory that I am going to carry at the next time is going to be exactly the memory that I had in the previous time, which is exactly the one computed directly from Julia, right? So if I have ut every single next time to be 0, this means that I computed the memory on Julia, right? And then I copied it every single time next, right? Now, if I get to the point where if I get to the point t, or t plus 1, where I want to compute the or find out, predict the next word, I am going to use the memory that I have at time t, and that memory at time t has been copied all the way back to the Julia word, right? So it's going to have very fresh information about Julia, right? Everybody's clear? So it's going to have fresh information about Julia. This means that your neural network is really seeing Julia, right? And it makes sense now for your neural network to be able to just give the right pronoun. Yeah?
In the second step,
right.
when we are doing 0 times h tilde e,
right?
wouldn't that make us not remember anything from the current word and only remember
The current word, right? We are ignoring it.
don't we need to?
If you have a sentence, lots of words are redundant, right? Yeah, you can't, I mean, this is the key point. I mean, of course, you cannot be very selective. I want to remember Julia, I don't want to remember the name of the university, for instance, right? You cannot select this, but you can say that for, is, at, these these like basic words, right? You can drop them. Articles, the, a, all of them, you can drop them, right? Right now, if you just do basic RNN, it doesn't find it out, right? It just treats everybody as a part of memory, right? And those guys are going to limit your memory because you want to get also some information about is, a, the, all of them, right? But when you have this option to be selective, right? You can drop them and you can just carry information about UDA, the name of the university, the name of the award, and so on, right? Make sense? Questions? So, you got the idea what we're doing? So, we are having this U, and this U is going to let us to remember or forget something, right? And that is the key point. If I want, as I said, if I want to just compute the new word or predict the next word at time t, then I need to know HT. I'm going to use HT, and HT is going to be directly connected to UDA because I have made my neural network to just ignore anything between UDA up to the point that I had been, right? Now, one thing that you might ask me here is that, well, this is intuitive, but how does it impact the vanishing gradient, right? And then you can think again that you are somehow doing a skip connection, but in time. And as you remember, when we did in chapter 5, when we were dealing with the deep neural network, we said the trick is to just do a skip connection. And that skip connection is going to just send you some gradients, right? You're actually doing a skip connection here, but this time over time. How is it the case? Well, I am computing the gradient of hi with respect to the weight, right? And I told you this derivative is derivative at time hidden state at time I minus 1 times the derivative at time I minus 1, right? But if I have that u and I have skipped everybody in between, how does the gradient at time t look like? It's going to be the gradient of the hidden state at time t0, right? Because I ignored everybody in between, right? So when I have that kind of skip, when I said u equal by 0, the thing that is happening is that this h gets multiplied to that u. It becomes 0, right? And this derivative is getting exactly the previous derivative, right? Because I copied the same memory, right? Memory at this time, the derivative, as long as this is exactly the copy of previous time, is the derivative at that time, right? And so on. So it's like a skip connection, but this time it's happening in time, and it can help with vanishing gradient. Make sense? Questions? No question? Okay, great. Now, one question that you're going to have, so first of all, this U guy that you see here, it is what we call it gate. And the name totally makes sense, right? It's just like a gate, like a tap, right? You just let some information go, you're going to block the information whenever you want, right? And you usually keep it between 0 and 1. If you make it 0, this means that you block the information. You're going to take whatever information you had before. If you make it 1, you're going to just copy the complete fresh information. You wipe the memory you had. If you set it something in between, then you are just doing a kind of balance between these two approaches, right? This is what we call a gate. And how we can design a gate? Well, how we can get this gate? Any idea how we should do it? Yes? Exactly. You just design one module which looks like the gate that you want. You give it a bunch of weights and you let it just get trained, right? This is how you do it always in deep learning, right? So we are going to learn it obviously, and how we can learn it? Well, we can just design one module which is looking like a gate. Okay, if I have one information x at time t, and I have the hidden state at time t minus 1, then this is the whole information I have in one particular time, right? I can go ahead and multiply them with a bunch of weights, right, which I can learn, and then I could potentially add a bias here as well, obviously, right? And then once I have this, I just activate it. And I want it to be between 0 and 1. What should I use as activation? Sigmoid, right? I'm going to use a sigmoid as an activation. It's going to be a gauge, right? And how do I know what should I choose to be W and these two different weights inside the gauge? Well, I just leave it to get trained using gradient descent, right? Make sense? Questions? Everybody's cool? Great. So, obviously, you need to use sigmoid. The sigmoid reason is that you want to keep it between 0 and 1. Of course, if you just have one bounded function, you can do it as well, but sigmoid is the most conventional one, right? That's one thing. And what about the dimension of this gauge? How should I set this dimension? Because when I have my input and my hidden state, I multiply them with a bunch of weight, I compute a bunch of features out of them, right? How many features I need to compute? Well, it depends what variable in your neural network you want to gate. If you know which variable you want to gate, you're going to set the dimension exactly same as that one, right? Then it's going to be a bunch of numbers, same dimension, all of them between 0 and 1, and then you can multiply them entry-wise, right? And then you gate everybody inside that object, right? Everybody's cool? Questions? No question? Okay, there are two different gated architectures. One of them is GRU, gated recurrent unit, and the other one is LSTM, long short-term memory. Now, GRU is the simpler one, LSTM is the more complicated one. And you expect GRU be the one which is older, right? But no, this is not the case. Actually, LSTM was proposed long before people start to understand what is gating. So people worked a bit with RNN, they just left it because it was not working, and people kept on working on some other things, right? And there was one master's student in University of Munich. He just did his master thesis. In his master thesis, he came out with the idea of LSTM. And he did not call them directly gate. He said, like, we can have these extra modules, and then if you put this extra module, it's going to get better memory on a text. He did his master thesis. He submitted. He got his degree. He did his PhD. He became a professor. Nobody even cared about that. Till people started to get more serious about recurrent neural network. And his prof, who was a quite well-known computer scientist, he told everybody, oh, come on. Years ago, my master's student has done this, and it's working. It's just expanding the memory. And people started to look at this, and they said, oh, he's doing something like gating. Let's call it gating, right? And let's try to understand whether this is really what's happening or not. Then they designed GRU, a simpler version. And they saw that it's working as well, and they said, oh, Schmidt-Huber actually did gating, right? And it was long after he finished everything, he was having his own PhD students, that he got known for what he did during his master. So that time he didn't call it gating, but essentially he just proposed the whole principle. Now, when it comes to the gated units, we usually only care about the hidden state, hidden layer. And there is a kind of classical diagram to represent that hidden layer. I'm going to show you that diagram, and I'm going to explain you how you can read that diagram. But that diagram is going to help you much easier to represent any gated architecture. Now, in order to start with that, I'm going to start with showing the basic RNN. The basic RNN is the element-like network, right? So your hidden layer is just a linear computation and activation, right? And you don't really care when you talk about these gated architecture. You don't care, of course, you never care about the input, right? You never care about the output as well, because once you know what is the hidden state, you can compute the output, right? You even don't care about the depth, because you would say, if I want to make it deeper, I'm going to copy the same module on the top, right? The only thing that you care is that what is exactly happening inside this hidden layer, right? So this is how we show it when we talk about recurrent neural network or gated architecture. And let's start with the basic RNN. So in the basic RNN, The input gets multiplied with its own weight, hidden state, its own weight. You do the computation, and that's the guy that goes up, right? Goes to the output layer. Now you can do whatever you want in the output layer. You can either compute a fully connected layer and get your output, or maybe you want to process it further, right? We don't care about that, okay? Now, how can I show this? Like, as I said, X goes in, H from previous time comes in. This guy is your hidden layers computing your new hidden state, right? And that guy goes up. You don't care too much about this one. The main thing that you care about is this yellow box, right? You want to know what is happening inside this one, right? And for the basic RNN, you do know what is happening inside it, right? It's just basically one fully connected layer, right? Everybody's cool? Okay. Now, yeah, so basic things that we want to specify: how does this unit look like, how it updates this hidden layer, and how it's going to pass this hidden layer to the next time, okay? Hidden state to the next time. Now, for now, you assume that we have only one hidden state, but I'm going to explain you LSTM, and it has more than one hidden state. But for now, just let's think about a simple case. Now, this guy is the basic RNN, and how you can read this diagram. In this diagram, your hidden state from the previous time is coming in, right? This guy comes, your input goes in as well, right? Each of these lines, they are carrying a weight, okay? So this guy has its own weight, this guy has its own weight. And when they just intersect, you add up whatever computation you have done, right? So when you see that X comes and meet H, it means that it had its own weight, this guy had its own weight, they added up, now you have the computation here, right? Everybody's cool? So I'm going to drop those weights, I'm going to drop the summation to just, intersect the lines. This way, it's going to make the diagram much easier, right? And then these guys come here, get activated with tan H, because we like tan H, and then it's going to pass to the next time. Make sense? Yes? So it's the same diagram, same thing that we had before. We just show it with this new diagram, this new way of representation. Okay? Now, first, let's think about GRU, the first gated architecture that we had. It's a bit different from the one we had in the basic RNN. So here we basically have two different gates. And you can go ahead and design a layer with billions of gates. I mean, obviously that is a nightmare to train that guy, but you can do it, right? It's totally based on your intuition. Where you want to gate, you just do the gating, right? But probably you need to have a reason for gating that particular variable, right? Now, here in GRU, what we do, we compute two different gates. One of them is the update gate, right? Which is, as you see, it has its own weight, right? Look at it here. I have W update, right? This one, which is the reset gate, it has WR. That is a different weight, right? Every weight inside this sigmoid is a separate weight. It's going to get updated by its own, right? So they are not sharing weights, okay? Now, this update gate is looking at the input previous hidden state, and it's going to compute you some gating variable, right? The reset gate is also looking at the input and the previous hidden state, and it's computing also another gate, right? Now you're going to use these gates to specify your output. How you do it? First of all, you compute one fresh memory, right? It's H till T. This is computed with a bunch of new weights from the input and a gated version of your previous hidden state. Now, what does this reset gate do? It can kill the previous memory, right? If I set this green gate here to be 0, it's going to get multiplied with the previous memory. It's going to kill that, and whatever I compute is just in terms of the my most recent input, right? Make sense? If I keep it completely open, 1, then this is going to be exactly as we had it in the RNN, right? The basic RNN. And if I keep it somewhere in between, this means that I'm going to just take a part of information from before, right? Everybody's cool? Okay, so you're going to gate your previous memory, and then you update your fresh memory. Next thing that you do, you have this previous memory, you have the fresh memory, and you compute the moving average using the update gate, right? Again, you can see if you set the update gate to be 1, completely open, you're going to send only the fresh memory, right? If you set update gate to be 0, then you are going to kill the fresh memory and you are going to copy your previous memory, right? And then now you have your hidden state out, right? So you have your hidden state out. You can either give it to the output layer to compute the output if you want to do further processing. Maybe you want to have exactly one other unit like this on top. You can do it, right? Just instead of input, you're going to give that unit HT, right? Everybody's cool? Questions? Clear? Okay, now, yeah. Now, we can represent this gate in this form, right? And right now you see why I use this diagram, because it's going to make life much easier as compared to showing all the, connections like what we used to do in deep neural networks. Now, it looks a bit complicated, but it's really not complicated, so I can break it down simply for you. So the first thing that you're doing, you're computing an update gate, right? So input goes in, hidden state comes in, they have their own weight, they get superimposed, you just compute the weighted sum, and then you activate it by a sigmoid, you're going to get your first gate, right? The other gate that you have, the recent one, is the same thing, right? Same guys come in, they have their own weights, added up, activated, right? It's your second gate. And now the next thing that you do, you are going to get this gate, multiply with your previous hidden state, right? You add up your input with its own weight, and then you do the activation, right? This is the fresh memory you compute, right? And when you want to pass it out, what you do, you would say the update gate that I have, I'm going to do moving average. 1 minus this guy, and this guy itself. The guy is multiplied to the fresh memory. 1 minus that gate is multiplied with the previous memory. They add up, give you the new hidden state, right? Everybody's cool? You see that? So you don't really need to panic when you see this guy. Essentially, you have one reset gate here, you have one update gate here, and the rest of it is just computation, right? Basic computation, right? But it's going to be easier to show it this way. Everybody's clear? Questions? No question? Okay, great. So if you got no question, let's then take a look at the, okay. So, yeah, I mean, if you want to think about GRU, then you're going to have GRU only here in the hidden state, right? So this is the process happening in the hidden state. Your initial state, you initiate it, for example, randomly, with the first entry in your sequence go inside the GRU. All of those computations I told you going to happen, you're going to get the first guy, right? And then you have this one, you're going to pass it again to the same GRU, right? And you're going to look at the next input, you're going to compute the next hidden state, right? And it keeps on going towards the end, right? Okay. Everybody's cool, right? Now, what about backpropagation? The backpropagation guy is coming back, right? So we're going to do all the details of backpropagation. Just joking, not doing that. Yeah, I just want to explain you that you can do backpropagation, right? Now, you can go ahead and do backpropagation if you are looking for the gradient for one particular weight, right? And now you have tons of weights here, right? There are weights for gating, right? There are weights for computations, direct computations of the features, right? So all of those, each of those weights, if you just select one of the weights, say call it W, and you want to take the derivative, you can always go ahead and write the chain rule, right? You would say, I want to know the derivative with respect to W, so I'm going to take the derivative with the output times derivative of output with respect to that weight, right? And then I go ahead and look at my output. Okay, my output is written in this form. For instance, that weight is not the weight of the output. It's inside the hidden state, right? So I'm going to go ahead, write again the chain rule. The derivative with respect to hidden state times the derivative of hidden state with respect to that weight, right? And I can keep on going like this. Well, maybe I am looking for the one weight inside the gauge, right? What should I do? Okay, my hidden state is written in this form. So I'm going to write it down again by chain rule. I'm going to say derivative with respect to the gate times derivative of the gate with respect to that weight, right? Plus derivative of my derivative with respect to previous memory times derivative of the previous memory with respect to weight, right? Plus derivative of the fresh memory times derivative of the fresh memory with respect to the weight, right? And you keep on going like this, right? So I do know it's going to be a mess. I do know that nowadays you have it in PyTorch, but good old days, people used to write all of it down, right? To find out how they can backpropagate, then you can implement it, right? But it's doable, always doable. If you cannot do it, then that neural network is worthless. Throw it away, right? You should always be able to backpropagate, obviously, right? Questions? No question? Okay, yes?
In that diagram, it looks like a weird short circuit. That's kind of confusing.
What? This one?
Yeah. The gamma are the result of the multiplication. Which line is the result of the multiplication?
Here, down, this guy. This one. This one comes again and adds up, right? Yeah, just like this. This one, right? Questions? Yeah.
So once the reset gate is active, we just reset all the memory.
Exactly.
So
It's like,
we cannot control how much information.
yes, it's like beginning of sentence, right? Yeah, I don't care any more about it. I want to reset the whole memory, right?
Yeah, so the next update gate just get input for the next state.
Right, right. Questions? Okay. Great. Okay, now LSTM, the most practical one. By the way, did you know the very first version of language models were implemented? I mean, the commercial ones where people started to talk with was implemented by LSTM. I'm not sure if you were aware of language models at that point of time, but there had been like...
The Google Assistant before Gemini?
Yeah, I'm not sure about Google Assistant, maybe, but OpenAI, when they started thinking about building a commercial language model, first they worked with LSTM. But then, of course, GPT came out, and then they had Transformer, right? So 2017, Transformer was proposed. 2018 on, everything got Transformer, but before that, anything you had which was capable of communicating with you were implemented by LSTM. Okay, so now, let's get to LSTM. So LSTM has more gates. It has 3 gates, forget, input, and output gate. It has one other difference. It has 2 different hidden states. And one of the hidden states is only used to update your hidden state. The other one is the one which is passed to the next layer. So the one which is passed to the next layer is what we call it hidden state, and the one which is used to only update, we call it cell state. It's just for that cell. It's not used for the computation of the output or the next layer. So we have 3 gates: gate forget, gate input, and the gate for output, and each of them is exactly computed as before, right? So you look at your input, previous memory, and you do this computation activated by Zigmund. Now, then you are going to update your actual cell state. So the actual cell state is a kind of fresh cell state, and that fresh cell state is again computed from the previous hidden state and your input. So this actual cell state, if you look at it, is essentially the kind of computation you used to do in the basic RNN, right? And you take it as the new hidden state, right? But now you're going to take it as the cell state, Now this cell state is going to get multiplied with this new fresh cell state is going to multiply with the input gate. So if the input gate is open, the cell state is going all the way in, right? If the input gate is closed, then the cell state, your computation, is going to be blocked, right? You also have a separate gate, which is the forget gate, and that one is getting multiplied to the previous cell state, right? If the forget gate is 0, then you forget everything, right? You don't remember anything from previous cell state, but if the forget gate is completely open, then you are going to get all the previous cell state into your computation, right? And now the next thing that you do, you compute your output by gating an activated version of cell state. And this is not a very conventional thing that you might consider, but like it was totally experimental. As I told you, this was developed long before this idea came out, right? And then like the one who invented this, he just played with different activation connection, and it turned out that this one is working fine. So it's purely experimental. But the thing that they do in this architecture is that they get the cell state that you computed, which is somehow carrying fresh information, a part of fresh information, and part of previous memory, and then you are going to activate it, and again you gate it. Obviously, if you set the gate, output gate closed, then nothing is going to pass, right? And if you make it completely open, then everything is going to pass, right? Everybody's clear? Okay.
So even if the forget gate makes us forget everything,
Right.
Gamma 0 still has something from HT minus 1.
Yes, because of the your here when you compute the actual memory, you are taking HT minus 1 into account.
Also has it, right?
Sorry?
Gamma O also has it, right?
Gamma O also has it, right? Obviously, but for the gates, you should always think in terms of opening or closing, right? So it's gonna if it's completely open, you can drop it, right? Like approximately. And then this guy is going to carry all the information, right? But you are right. I mean, it's no way that I can kill completely the information from before. The main reason, as I say, is because they were trying to extend the basic RNN, right? Questions? No question? Okay, great. So if you got no question, then again, we can draw the architecture of the cell in this form. This is the diagram for the cell. And again, you have the forget gate here, you have the input gate, you have the output gate. You can break it down into all of those single computations that you had, right? Once you have hidden state, previous hidden state, your input, you do your first computation, right? That first computation is the fresh cell state, right? C tilde that we had. Now that you have this guy, then you are going to have your forget gate and input gate. They are going to participate in computation of the new actual cell state, right? So the actual cell state is the gated version of the fresh information you computed here, right? So this one was basic RNN, but now you're gating it, right? But that is your cell state. The next thing that you do, you're going to get your computation that you had. You are going to gate it. And once you gate it, you're going to multiply your cell state with you're going to activate your cell state and then you gate it, right? So the key difference to the conventional gating that we got in the other architecture is the second activation, right? Because this guy, CT, right, is basically the gated version of this guy, right? And this guy itself is already activated, right? But you get this one, and when you want to compute the next instant, you again activate it, right? It's a kind of double activation. It's a bit weird, but as I said, it was experimentally shown to improve the training. Questions? No question? Okay, so the naming is quite obvious for you, right? The forget gate is going to help you to forget whatever memory you had from before. You just close it, no memory is going to carry from before, right? The input gate, obviously, is going to gate the information, the new information that you're, or the new memory that you're computing, right? And the output gate is obviously just gating the output. You're going to let the output to go a bit or completely or not, right? Questions? No question? Now, one question from my side. Would you think there would be a problem if we just put this gate here? Because potentially this guy can kill completely the hidden state, right? A zero hidden state is useless, yes? Yes or no? Any answer to that? Does it harm the learning process? Yes, but when you want to pass it, you are going to pass only HT to the output layer. CT remains inside the cell. When you want to compute the gradient, you compute the gradient from the output, right? And then the one who is going to participate is H. Of course, when you get to H, then C is going to show up inside H, but in your first move, it's only H. Any idea? Do you think that is a trouble? Should you be worried about that? The answer is no, you should not worry about that, but why? Any idea? H becoming 0, can it stop your learning process? No, because H becomes 0 is not a big deal, right? The thing that is important is that your gradient is not 0, right? When you have gradient, you're going to update, right? If really you need information to come out of your cell, it's going to learn from data that it should be 1, right? The only thing that you should care about always is that, is there enough gradient that my network can go towards making it 1, right? And of course, this guy, this gate, is a sigmoid, right? Sigmoid always has gradient, right? You never get into this trouble. So H becoming 0 is not a problem. Gradient becomes 0 is a problem, right? So it's always the important thing you need to think. Like, I hope that all over these chapters, I have transferred this kind of mentality to you, that when you think about a computational model, at the end of the day, that's the gradient who is talking, who is doing the learning, right? And that guy should exist. Here it exists. There is no problem, right? Everybody's cool? Question? Okay, now if you do use LSTM to process a sequence, obviously you are going to start with the initial hidden state. For the solid state, again, you need to have an initial value, right? And then each time you are going to get your new hidden state and new solid state. The solid state is only remaining inside the cell for the next computation, right? And the guy who you are passing to the next layer is going to be the hidden state, right? So you're going to keep going in time every time the hidden state is going to compute the next layer output. So this is an important hint, attention, you should pay attention here that the hidden state is the guy who is going up. Okay, solid state remains there. But of course, solid state somehow shows up inside the hidden state, right? Because you compute the hidden state in terms of solid state. Any question? No question? Okay, if you got no question, then let me talk shortly about the backward pass. Now, if you want to do the backward pass, what should you do? Again, you need to write down the chain rule, right? I'm not going to open it up because it's going to be just a messy chain rule, nothing else, but just want to give you this idea. You always can do it, right? And if you are designing something totally new, probably even though you can do it by PyTorch, probably you want to write it down for one very basic thing, right? Basic case, right? Because you want to know that there is no weird module in between, which is killing the gradients that you have, right? This should not happen. And of course, if you want to compute the gradient with any weight, you start with the gradient of the output, and you keep on going backward, right? The output in terms of hidden state, the hidden state in terms of the gates, and then it depends which weight you are looking for, but you can always keep on doing the gradient step by step, right? Till you get there, right? Questions? Everybody's cool? If you would like, you can try doing it. Like old days when people did not have too much to teach in deep learning, they're going to do one session on backpropagation on LSTM, but it doesn't make sense anymore nowadays. Okay, great. So if you got now a question, then let me just give you a short overview on this idea of bidirectional sequence processing. So what we did up to this point, we designed one neural network, and that neural network is able to go over a sequence, right? Every time that it goes over the sequence, it computes a memory, and then it's going to update that memory, right? And this is going to help you that you talk about the future of this sequence every single time, right? But you do not necessarily need to process in a causal form one sequence, right? So it might be the case that you can learn from the future information in your sequence. And if that is the case, this architecture that we talked about is essentially not doing that, right? So it starts from the beginning of the sequence and it goes all the way towards the end, right? Each time that you want to talk about the or you want to look at the output, it can only talk about the future based on what it has seen past, right? Now, but it might be that you want to know, you can benefit from the future, right? For instance, maybe this is your sequence. This is a test that you want to do. You want to complete this blank point, blank spot. So the color, blah, blah, that many people assume is the color of sun. What is the answer? The color that many people assume is the color of sun. What most people assume is the color of sun? Yellow. Great. 5 points. Yeah, yellow, that's right, but sun is not yellow, right? Okay, so here when you want to answer this one, if you start from the color, you have no idea about the answer, right? If you want to predict that guy, you need to know sun, right? Sun is the key component in your sequence that carries the information. Obviously, if you want to answer this question by one neural network, your neural network should be able to see both future of this sequence and past of this sequence, right? And if you want to do that, the idea is here, so you can get information from the sequence here, from the future here. One thing that you should pay attention, some tests like this one, you already have both. Causality does not make sense, right? There's nothing like causality. Of course, if you are predicting the future price, that's a different story, right? But if you are completing this one, you're still dealing with a sequence, but you have access to future as well, right? Now, if that is the case, the main idea here is to do what we call it bidirectional sequence processing. This means that you start with one LSTM, for instance, from time 0, and you go forward. At the same time, there is one other LSTM, which is starting from the end of the sequence, right? And it's going all the way backward, right? And each time they are computing one hidden feature, right? So it means that if you think about one particular time t, then you are getting hidden feature ht, which is coming forward, right? So your LSTM started from very beginning, it just came all the way towards time t and computed this guy. There is the second LSTM, which started from the end of the sequence and it just came backward till time t, and it computed h prime t, right? And then you can combine this ht and h prime t as a new feature. Maybe you concatenate them, maybe you add them, maybe you multiply them, whatever you want, right? And then you're going to pass it to the output layer, right? Now, output layer, when it wants to talk about the output, it's going to see the information from past and future, right? And this is going to help it understand or give it more information, right? So this is the classical form that you do. Input goes in. Every single time you had one forward neural network or recurrent network, which is looking into the previous hidden state. The other one is looking in the future hidden state. They compute their own hidden states. Then you're going to merge the hidden states computed by these two, and then you're going to pass it to the output. Everybody's cool? So when you do that, this is bidirectional. In PyTorch, you have it for free. You just call LSTM, you put bidirectional true, it's going to do it. But behind the scene, there are two LSTMs going two directions. Okay? Yes?
Is the idea with this that we could potentially hit an early exit because you're looking both ways? So that we don't actually process everything, because once we see color from on the left side and sun on the right side, we can essentially predict that token.
That's right.
There's
That's
no
right.
reason to.
You could have one LSTM going all the way, and then you give that output, right? You can do that, but the problem here is that the one which is talking here, right? It is, it is going, the memory that you have in your sequence is going to be asymmetric now, right? So if that happens like your neural network could, for instance, have long future memory, short past memory, right? Depending on how the gating happens, right? But if you have it bidirectional, then you're going to get symmetric, right? Yeah. But your point is right. You can still do it theoretically with just one LSTM. You just need to go all the way over these sequences, right? And you need, now the issue here is that, the issue here is that if you run the LSTM at the time, like here in this application, when you run this guy, right, you should think about inference time. It's not about learning issue. You can't train that guy, which is also getting all the information in the sequence. That's right. If you want to build one language model, that's enough. But in this one, you want to complete this one, right? And this one needs to see this guy already, right? But your neural network, how does it work? It's just one LSTM, right? It goes over the first token, gives you the next token, right? Next token, the next token. When it wants to give you the next token, it has not seen sun anymore, right? When it goes all the way towards sun, then it only gives you the next token, right? Right? Unless you can make a kind of trick that when you get to sun, you tell your LSTM, no, give me the answer to that, right? Which is possible to design it that way, but it's very weird, right? It's going to be very restricted to this particular problem, right? It cannot solve any problem. But your idea is essentially right. You can still deal with designing one LSTM, but it's going to be a bit of trouble. Okay. Everybody's cool? So you essentially can use any architecture here. You can use GRU, you can use LSTM, you always LSTM. And when you do LSTM, obviously every single forward and backward LSTM going to have their own cell state, and you are going to merge them. Now, one thing that you might wonder is that how do I do the merging here? As I said, it's not that important. You can simply concatenate them, like put HT next to HT prime, and then you do the computation at the output. You can actually, for the merging here, you can actually do a weighted merging as well, right? So you would say I have the first hidden state, the other hidden state, I multiply them to their own weights and I add them up. Now I have another hidden state and then I work with this one, right? You can do it as well, right? It's not a big deal. So yeah, you can do that. And of course, nowadays you have access in PyTorch to the RNN. You have the basic RNN. When you write RNN, is essentially Elman-like network with just tanh. Typically, tanh is the activation. And you can use LSTM, GRU, and in all of them, you just need to set the bidirectional attribute to be true to become double neural network to do the bidirectional processing. Everybody's cool? So, and as I said, for the merging, there are some options, but usually when you use bidirectional version, in most implementations, you already get access to both the hidden features, right? And then this is your choice how you want to merge them. Classical one, people concatenate them, but you can do anything that you want. It does not really impact too much. Okay. Questions?
After merging them, like, does it just pass through one layer, or it can be any number of layers?
Any number of layers. So actually,
Can that also be recurrent, or
sorry?
can any of those layers also be LSTMs, or no
Yeah, definitely they are going to be LSTM. I mean, you can do multiple like time-independent processing layers. That could happen. But you can, again, do one other LSTM, right? So you have, if you want to think, just think about one particular time. At this time, you look at your hidden state, you look at your input, you compute the new hidden state, right? Now, you can put one other LSTM, and that LSTM looks at this hidden state you computed, its own previous hidden state, it computes its own new hidden state, right? You can keep doing it as much as you want, right? And then finally, you can give it to an output layer. You can do it as well that you get the hidden state, then the next one is not LSTM. It's just a simple feed-forward layer, right? 1, 2, 3, as much as you want, right? But typically, if you are dealing with a sequence, the one which you are caring about is the temporal correlation, right? The depth processing is not a big deal, typically in those tasks, where you use LSTM at least, right? And there, when you increase the depth, you basically just increase the number of LSTM cells, right?
What is the typical LSTM?
Not too much. You cannot do it too much because you're going to make it super complicated. Now, for each of them, you want to go back in time, right? And it's true that you are doing gating, but gating is only helping you not to vanish the gradient. It doesn't change the complexity. It actually increases the complexity because you have lots of gating weights, right? So you typically do not do it very deep. And to be honest, I don't know what is the deepest RNN implemented, like practically, but you can take a look online. But 1 or 2 layers is the most thing you always think. Like the basic sequence prediction always works with one single LSTM. But you can make it double. I mean, on your computer, 2, 3 layers, you can easily do it. But if you go even more, it's going to get more complicated, and also the training gets a bit unstable. Yes?
In the example of LSTM, you use sigmoid to activate, and you just said that that we typically use 10H to
10H, right.
activate. Is it like more beneficial?
Sigmoid is for gating. Yeah, and for gating, you always want it to be between 0 and 1. This is why you use. But for the basic computations or basic feature computation, yes, 10H is yes. I mean, I think if you make it very deep LSTM, that 10H is not very crucial anymore. It might be the case, but old days when people were, I mean, a bit was still a bit something, then people were using 10H. Questions? Okay, no questions. So I guess I do not have time to go over this part. This is a kind of bonus part, which I could shortly go over it. So if you look at the course page, I have here just 15 extra slides on this segmentation problem. And then there is one appendix, which is the complete illustration of CTC algorithm. Now, the key point that I want to explain here for you is that labeling a sequence is not always a simple problem. And it's going to somehow show up directly in your training process. The point is that if I have this image, right, and I want to go over this image, I cannot really know where each segment is finishing, right? At the end of the day, I am going to have one filter of fixed size, right? And this filter goes over this image chunk by chunk, right? And then maybe I have maybe the first couple of chunks are the first number, right? 2. The second couple of chunks are the second digit, 3, and so on, right? But then the question that shows up here is that, well, which output is corresponding to 2, right? Because my sequence is looking at the first chunk is a part of 2. It's not yet complete 2, right? The second chunk is the second part of 2. It's again not the complete 2, right? Maybe the third chunk is where 2 is finishing, right? And then I need to put 2 exactly at that point, right? But the question is that, how do I know where I put it, right? You see that? So that is the correspondence issue when you have a sequence like image a long image handwritten digit, and you want to go over it by an RNN, you really don't know where is your next label coming, right? And what you have in your data set is 23241, right? It's going to be a sequence of size 5, right? Whereas you can chunk your input as a sequence of 100, right? So these 5 numbers, where I should put them, right? This is the first question. The second question is that, what should I do with these empty outputs, right? Should I throw them away or can I use them, right? Now, the answer is that if you want to solve this problem naively, is an NP-hard problem. It means that you cannot solve it within polynomial time, right? Or polynomial time algorithm. You cannot do it. So, what you can do then, well, you should approximate it, but there is one very efficient way to do it, and that is when you put all the labels on a graph and you see that it's going to build a tree, so you have a tree search, and doing a tree search is not complicated as the naive approach, right? That is what we call it the CTC algorithm. Still, it's being used, especially in audio applications, because this is something very typical in audio applications. But I'm not going to go over too much of details. I just give you a short overview of the problem. If you would like to know exactly how CTC works, it's a bit of derivations. You can take a look at the appendix. Typically in nowadays application, you don't get to the point that you really need it. But if you get to need it, you can take a look at that one. When I give you the illustration, you probably get the idea of what is the issue and how we can use CTC. And then CTC, again, is pre-implemented in most platforms, so you really don't need to get all the details, okay? So I'm going to briefly talk about this, and then we start with the next chapter, seg-to-seg models, okay?